Okay, do you have any questions? Sure. Yes, we have to decide on a midterm date. So when would you like to have it?
Not the date, but in the period from the 11th to the 17th, I'm not.
Okay, so we should do it before then. So let me see.
Can we do it after? Would it be too late? Would it be too late if we do it after?
18th. Well, you see, after 18th, April, let's say it will be on the 23rd, we cannot do it. 24th. Well, then at the end of May, the semester ends. So that will be kind of too late. I'm more tempted to do it at the beginning of September, before you go. In the first half of April, sorry, not September. So when would you like to have it?
If it's before, it's fine.
Hmm?
If it's before, it's fine.
So you are leaving on 11th?
Yeah.
You are leaving on 11th, so what about the 2nd and 3rd? That is not this weekend, but the following one. Or no? Yes. Not this weekend, but the following one. Well, the exams I usually prefer to give you as much time as you like. So it will be like something like 3-4 hours. I mean, the questions you will probably be able to do them in much shorter time, but I just don't want you to rush. So if you want to think about questions, think about them. So that's why I prefer the weekends, because during the weekdays we have to do it. I mean, the lecture hours, they are not long enough. After 5:30, well, it's dinner time. It will be too late. So we are talking about the first midterm date. I was proposing to do it on the weekend of the at the beginning of September, April, 2 or 3, as you wish. Okay, just check it with. I mean, let's just fix it for the. Do you prefer the Sunday or Saturday? Yeah, I prefer Saturday because that Saturday I have another exam. So if you don't mind, I would rather have it on Saturday.
If I have to say, then I would prefer Sunday because I have another exam Friday.
Okay, so you want to have, okay, so Friday.
Monday maybe.
No, Monday no.
No, Monday.
One day in between. Okay, then Sunday.
Third.
Okay, he's not registered. Okay, so let's just fix it for the 3rd of April. And if something comes up with, I mean, there's the, okay, you're from the electronics department, right?
Yeah.
Okay, so you know their exam dates, fine. So probably 3rd would be fine for them to also, right?
Yeah, we don't have any exams.
No, okay, great. So first midterm. April 3rd. At noon, in our lecture hour. $13.40. Okay, so we decided on the midterm date. It's on the 3rd of April, Sunday, at 1:40, our lecture hour. So the second midterm will probably be at the first half of May. And we can determine it later on. And then we have the final. And the subject, everything we do until that date. I mean, it will be like 3 hours. I mean, 3 hours in the sense that you are already having your homeworks. The basic idea of the homework is so that you learn the material. I mean, if you have realized, I don't really solve that much examples in the class. And I don't really think that makes too much sense. You have to do the exercises. Otherwise, I mean, just watching me doing the examples will not really help you learn. So you have to do the exercises, so that's the point of the homework. Now, the point of the exam is that I ask usually one long question, such that you have to do the derivations. The other ones will be mainly to test whether you learn the basics of the basics of the material. You should be able to finish it in much less than 3 hours, but I just don't want you to rush. And if you want to take your time, just take your time in the exam. I mean, even 3 hours, we can extend it further. Okay. Any long formulas, I will either ask you to drive it or I will give you a formula sheet, so don't worry about the formulas. If you need any formulas, I will just give you one. Just ask me, I will tell you, or tell you to drive it.
This is Sunday, not this week, but...
Not this weekend, by the next weekend. Now, this weekend we have the lecture. We will also have the lecture that we were supposed to do 2 days ago. And then we have this exam in the following week.
Did you get my online?
Yes. 7 pages, scored pages, yes. In shuffled order.
It wasn't mentioned. That's because I guess the first half was after Friday night, then the second half. So,
I got them. No. Okay, any questions about the midterm?
The Friday before the midterm is included, please.
No. Well, you see, if I say no, you will not study it. You will
not be able to digest it.
Well, let me put it this way. If I ask something about the material that we do on Friday, it will be something simple. Let me not exclude it completely, but I might include some question which will be a simple one, which will not require you to digest it deeply. And most of the time, my exams are out of 120 points. So you have 20 points bonus. Okay, any questions about the material that we have been covering?
did you finish WKD?
Yeah, for me, yes. The next we can do is just to do some exercises, but that's in your homework.
Will be dealing with scheduling?
No, not yet. I mean, we first need to study. Up to now, we have been doing time-independent problems. So we were looking at the eigenvalues and the eigenfunctions. Of course, eigenvalues and eigenfunctions, they tell us a lot about the system, but they're not the whole story. So, for example, if you are interested in lasers, what you do in a laser, what happens in a laser is what we call the stimulated emission. So you have an atom, and there's a light acting on the atom. So that light kind of acts like an external time-dependent potential acting on the atom. And since the frequency of the light will match the transition frequency of the atom, then it's more probable for the atom to emit a photon just in phase with the photons that are already existing. That is how a laser works. And for such problems, we need this time-dependent perturbation theory. So up to now, we were dealing with potentials that were time-independent. Now, what happens if the potential is time-dependent? Now, another point of view is, I mean, usually we don't create eigenvalues, energy eigenvalues. We create states that change. If you consider, I don't know, like a scattering experiment in the LHC, what you do is you just create some wave packets, which are not energy eigenstates. You send them and you look at how the wave packet changes in time. So that is what tells us what the potential is, how the system is interacting. So also for such problems, we need the time evolution of a wave packet, the time-dependent wave functions. Now, of course, whatever wave function you have, you can always write it as an expansion in terms of the eigenstates. Of course, if it's not a time-dependent one, if you don't have a time-dependent potential, you can always write it in terms of the time-independent energy eigenstates, and then you have this energy time-dependent factor and some coefficients. You sum over all, and these coefficients will be independent of time. And we can use the time-independent perturbation theory to calculate the modifications in psi and the energy eigenstates and the energy eigenvalues, and to see how the time dependence will be modified if we have something else. But another thing that will be kind of tedious, because if your initial wave function has many eigenstates in its superposition, so that will be you have to calculate the correction to all of them. It will become tedious. Now, for simplicity, let's just start with what's called a two-state system. We have a two-state system. A two-state system is basically a system which can be either in a state A or a state B. So this is our basis. And of course, these are the eigenstates of H0. So this is our unperturbed Hamiltonian. Now we add the perturbation to this one. H will be H0, H0 plus H prime, which can also depend on time t. Now H0 is a Hermitian operator, so its eigenfunctions are form a complete set. So whatever your function is, in this case, whatever our state is, we will be able to write it in terms of their superposition. If h prime is 0, we will also have this e to power minus I over h bar EAT and e to power minus I over h bar EBT. We have this oscillating part. And then we will have some constants. Let's say this is the wave function at time t. We have the Ca of t, Cb of t. Furthermore, we know that if h prime is equal to 0, then Ca of t and Cb of t, they should be independent of time. So we are kind of separating time dependence into two parts. It will kind of simplify our discussion in the sense that H0 already makes our system to evolve in time. So if you are not studying an energy eigenstate, it will be changing in time. And that change in time will be given by, will be due to these exponential factors, e to power minus I over h bar, the energy times the time. And then there is some additional time evolution due to the presence of this h prime. And this additional time dependence, we just put them in these coefficients Ca and Cb. And there is nothing that prevents us to include these exponentials in our definition of the coefficients, but we can also separate them. So this is our solution. And we want this wave function to satisfy this equation. H psi of t should be equal to I over h bar del by del t psi of t. This is our Schrödinger equation. So our next task will be to determine the time dependence of these CAs and CBs. And in fact, what we will be doing is we will just replace this wave function in our time-dependent Schrödinger equation. We already know the time dependence of the exponential. It will be canceling some H0 terms, and we will obtain two equations, two differential equations for CA and CB in terms of various matrix elements. That will be our strategy. So let's just put the solution here. So Hamiltonian acts on the states, not the coefficients. So h of the left-hand side is nothing but Ca e to power minus I over h bar Ea of t, h0 plus h prime a plus Cb e to power minus I over h bar Eb of t, h0 plus h prime b This is the left-hand side. On the right-hand side, the only time dependence is either in the exponent or in the coefficient Ca and Cb. The states A and B, they are time independent. So if you just take the time derivative, we have I over h bar Ca dot e to power minus I over h bar EAT A minus I over h bar EA Ca e to power minus I over h bar EAT A. This is the derivative of the first term. And we have a similar term for the second one. Plus Cb dot e to power minus I over h bar, the exponent, EBT B minus I over h bar EB Cb, and the exponent B. Now there will be some cancellations. Now let's look at the H0 term over here. Remember, A and B are eigenstates of H0. So H0 acting on A just gives me EA. Now if you look at this term, this should be equal. I times minus I just is 1. Oh, I forgot. This is wrong. H bar is on the numerator. So H bars cancel. I times minus I is 1. So I have EA CA, the exponent times the A state. Here also CA exponent times EA times the A state. So they just cancel each other. This term and this term, they cancel. A similar cancellation will be for the B terms. So this term and this term will cancel. Well, that is kind of expected, because if you look at what remains, on the left-hand side we have terms proportional to H prime, and on the right-hand side we have terms proportional to the derivatives of the coefficients Ca and Cb. And we know that Ca and Cb, they will be time dependent only if H prime is non-zero. Because in our original definition, if H prime was 0, then the time dependent, the Ca and Cb should be constants, independent of time. That is why we separated these exponents. That is the time dependence in the absence of H prime. So let me just rewrite this equation. We have Ca e to power minus I over h bar E A of t, h prime acting on A, plus Cb e to power minus I over h bar EB of t, h prime acting on B. This is equal to I h bar Ca dot e to power minus I over h bar EAT A plus I h bar, the same thing for B. Now to get the Ca, that is nothing but the coefficient of A state. So in order to obtain that coefficient, we just take the inner product with the A state. So if we just do that, then we obtain I h bar Ca dot e to power minus I over h bar EAT. This will be equal to, and this is what remains on the right-hand side. And because A and B, they are the eigenstates of a Hermitian operator, they are orthogonal to each other. So overlap of A and B is 0. They are normalized. Overlap of A and A is 1. So this is what remains on the left-hand side. On the right-hand side, we have Ca e to power minus I over h bar Ea of t, A h prime A, plus Cb e to power minus I over h bar Eb of t, A h prime B. So this is what remains. And we can do the same trick for the B state, and that would give us I h bar Cb dot minus I over h bar Eb of t. This is equal to Ca Ea of t B h prime A plus CB e to power minus I over H bar EB of T B H prime B. And we can move the exponent to the other side. Now when we move the exponent to the other side, let me rewrite this in a different form. CA dot will be equal to minus I over H bar CA A e to power minus I over H bar H0 of T H prime. Now this is plus e to power minus I over H bar H0 T A. What I obtained, the first one, when I move this exponent to the right hand side, it becomes a plus I over H bar EAT. That is this term over here, H0 acting on A gives me EA. And when this H0 on the right of H prime acts on A, it gives me e to power minus I over H bar H0 of T. It gives me this one. Well, they will cancel for this state, but let's just keep it. I mean, for this next one, it will be non-zero. Minus I over H bar CB A e to power I over H bar H0 T H prime e to power minus I over H bar H0 of T. Again, the same operator. And it takes care of whether we have the EA or EB with a plus or a minus sign. Now we can do the same trick for CB dot. And CB dot will be equal to, again, minus I over H bar B e to power I over H bar H0 of T H prime e to power minus I over H bar H0 of T A C A plus, no, minus I over H bar CB B e to power I over H bar H0 of T H prime e to power minus I over H bar H0 of T times A. Let me rewrite it in a different form. D by dt CA CB. This is equal to minus I over H bar e to power I over H bar H0 of T H prime e to power minus I over H bar H0 of T. This is now a 2 by 2 matrix. Not the operators, but the matrix corresponding to that. CACB. Now, do you remember Schrödinger picture, Heisenberg picture of quantum mechanics? Now, in the Schrödinger picture, what we have is eventually we need to calculate the matrix elements of states and see how those matrix elements evolve in time. So the question is, why do these matrix elements evolve in time? Well, you have two pictures. Okay, hold on. You have these two pictures. You can say that, okay, my operators are time independent, but my states are evolving in time. So this is the Schrödinger picture. We talk about the time independent wave function. Or you can say that your states are time independent, but your operators are evolving in time. So this is called the Heisenberg picture. And then there is another picture called the interaction picture, in which the states are evolving in the unperturbed Hamiltonian, whereas the operators are evolved due to the perturbations. So you divide the Hamiltonian into two, just like we did over here, H0 and H prime, then your states are evolving by the unperturbed Hamiltonian. Well, that's why we took out the exponentials. And then the operators are also evolving in time here. Yes, your question.
The BB olabilir mi? C'nin
EA.
B cat'le başlıyor. Ek
Bir yukarıdaki de eğiliyor.
Where?
olabilir mi?
Oh, yes, they are B's. No, hold on. So what did I do here? B, A, B, B. True. Okay. And this is called usually H prime I. I, just to denote that, is the interaction picture. And even if H prime is, there's nothing here that tells us that H prime should be time dependent. H prime can be independent of time, it can depend on time. Everything here up to here is valid. But even if H prime started out to be time independent, H prime I will have time dependence due to these exponentials that depend on time. So this is the equation that we have to solve. Let's say H prime I T C. And what else do we know? We know that C, let's say we can say that initially, or C at t equal to 0, let's just say that this is C0. That's enough. I can formally solve that equation, just integrate both sides from 0 to t. And what we would have is the C of t is equal to C0 minus I over H power from 0 to t H prime I t prime dt prime times C of t prime. Of course, in this form it's not any different from the previous differential equation. But we can do one trick over here, called the solution by iteration. So C of t should satisfy this equation. So we should put this equation over here, which should still satisfy that equation. So that would tell us that C of t is equal to C0 minus I over H bar from 0 to t, let's say dt1, H prime r t1. Now instead of ct1, I just use this equality. And that equality tells me that it is C0 minus I over H bar from 0 to t1, let's say dt2, H prime I t2, C t2. This is equal to C0 minus I over H bar from 0 to t dt1, H prime I t1, C0 plus minus I over H bar squared 0 to t dt1, 0 to t1 dt2, H prime I t1, H prime I t2, ct2. And if you want, you can repeat it. But the advantage of doing this, we didn't get a solution, but you see, the first term is of the order of H prime. If the interaction is small in some sense, the first this is a term that is of the order of 1 in smallness. The next term is a term of the order of 2 in smallness. And if you just iterate this, you will get a correction that is of the order of 3 in smallness, etc. And if depending on how precise the result you want, you can just cut this expansion. And it gives you the solution, approximate solution. So this is where the perturbation comes into the game. So if you do this, if you calculate this exactly, there's no perturbation. If you cut it at some place and add the corrections one by one, that's what we call the perturbation. Can you guess the next term? Zero to t, t1, dt1, dt2, h prime I t1, plus minus I over h bar squared from 0 to t dt1, 0 to t1 dt2, no, this is just 1. Over h bar cube, 0 to t dt1, dt2, dt3, h prime I t1, h prime I t2, h prime I t3, c0. The next one will be to the fourth, 4 h primes to the fifth, 5 h prime. So this will be equal to minus I over h bar to the power n dt1 up to dt n, and dtn integral goes from 0 to tn minus 1, dt1 goes to from 0 to t, h prime I t1, h prime I tn, acting on c0. We can do one more step further. Let's look at the second one only. dt1 from 0 to t, dt2 from 0 to t1, h prime I t1, h prime I t2. Let's look at this one. May I change the order of integral? How can I do that? Now this will be equal to dt2, dt1. What are the limits on t2 integral? 0 to t. The t1 integral? You see, t1 is always larger than t2 if you look at the first line. So t2 should start from, no, t1 should start from t2 up to infinity. Or if you would plot the domain that you are integrating, no, not infinity, t, sorry. This is t1, this is t2. The first limit, t1 goes from 0 to t. And this is t1 is equal to t2 line. And then for each value of t1, t2 goes up to t2. So this is the domain of integration. You are integrating over that triangle. You can just go from, you can also, in this reordering, you change t2 from 0 to t. For each value of t2, you start from t2 and go up to t. And then we have h prime I t1, h prime I t2. Let me just relabel them. 0 to t dt1, from t1 to t dt2, h prime I t2, h prime I t1. In the last line I just relabeled them. Well, it would have, if h prime were commuting, h prime t1 and h prime t2, if I could change their position, then it would have been nice because I could have just add the left-hand side and the left-hand side and the right-hand side and divide by 2. Because what I'm integrating over would be equal, then it would have been great. In any way, I can still do that. I can say that from 0 to t dt1, 0 to t1 dt2, h prime I t1, h prime I t2, this will be equal to, I will still add the left-hand side and the right-hand side, integral from 0 to t of dt1, integral from 0 to t of dt2, but inside I will have h prime I t1, h prime I t2, if t1 is larger than t2, so that will give me the left-hand side, because this makes sure that t2 integral goes up to t1, and I have the left-hand side plus h prime I t2, h prime I t1, theta if t2 is larger than t1. This gives me the right-hand side, so I need to divide it by 2 also. So these step functions make sure that my theta 2 integrals, my t2 integrals are in the right domain. Now let's look at these ones. So we have these two operators, h primes, evaluate at different times. We have to multiply them. At equal times, they are the same operator, they will commute, but at different times, they might be different operators. So they need not commute with each other. But in this square brackets, so the one that comes early, in the first line, it is the t2 is earlier than t1. In the second one, it is t1 earlier than t2. Whichever one is early, it acts first. So that's why it's called the time-ordered product. So this is called as the square bracket, all of it is usually denoted by t, h prime I t1, h prime I t2. This is the time-ordered product. It's defined for any arbitrary operator. That depends on time. What it tells you is that you should just act the operator that is earlier first. That is what this time ordering is about. No, and the ordering inside the time ordered product doesn't really matter, because it's the time ordered product that tells you which order you should act the operators. Well, let me also put a factorial over there. 2 is just 2 factorial. Now, I will not prove it, but you can make the general proof that we have this up to t dt1 from 0 to t n minus 1 dtn of h prime I t1 h prime I tn. This is nothing but 1 over n factorial integral from 0 to t of dt1, 0 to t of dtn of the time-ordered product. We don't need to worry about the limits of the integrations. They are all from 0 to t, but the only thing we need to change is inside what we are integrating is not just the product of these operators, but their time-ordered product. So time ordering will just take care of the rest. Well, let us just define one more property. I mean, this time-ordered product is our invention. So let's just define it to be linear. Just meaning that if you have, let's say, A plus B, A and B can be any product of operators. This is TA plus TB. So this property tells me that I can take the time-ordered product out of the exponents, out of the integrations. So in particular, 0 to t of dt1, 0 to tn minus 1 dtn, h prime of t1, h prime of tn. This will be equal to 1 over n factorial, the time-ordered product of 0 to t dt prime, hi of t prime to the power n. Because once I take out this time-ordered product, the integrand is just a function of t1, a function of t2, a function of tn. I can just separate these integrals. And then each one of those integrals is the integral of h prime from 0 to t. And I have n of them, so that's why I have the integral to the power n.
You said time-ordered product is linear, but what are the arguments? A and B are those...
Any functions, any products of operators. In fact, any operator. Then the time ordering the product is just a normal product. I mean, you see, this h prime, well, if they are time independent, there's no problem. But you see,
How do they go into the time-ordered product?
so the ordering doesn't matter. Well, you see, what is the case in which they are time independent? So we define the h prime somewhere over here. If h prime commutes with h0, then they are time independent. Well, if they are time independent, that means at any time, I mean, all of them commute with each other, so the ordering doesn't matter.
So the integration limits from 0 to t.
I don't care, because the integrand is time independent anyway. If the integrand is time independent, you just take them out of the integral, all of them. So what remains in the integral is nothing but some c numbers, and the time-ordered product of c numbers is just the commuting numbers themselves. Well, I will do one more trick. Not trick, but I mean, with these definitions, remember what our c of t was. It was just sum from n equal to 0 to infinity of minus I over h bar to the power n of these things, and which we show that they were 1 over n factorial, time-ordered product of 0 of t dt prime, h prime I t prime to the power n, acting on C0, which is the time-ordered product of the exponent minus I over h bar 0 to t dt prime, h prime I t prime. Yeah, we have a short way to write it down, but the usefulness is something else.
Try to diagonalize.
Hmm?
You will try to diagonalize to take the exponent or something.
Well, you will not need to. So, I mean, toward the end of the semester, probably not this semester, but if you take the quantum mechanics too, you will do field theory, some kind of introduction to quantum field theory, or if you study quantum field theory on your own, usually this is where you start from these time-ordered products. These time-ordered products have some other nice properties which allows you to calculate any correction at any order without doing all these derivations, summations, etc. And if you have heard of Feynman diagrams, the Feynman diagrams, they start from these time-ordered products, the properties of these time-ordered products. Now, we will not proceed along these lines, but I just wanted to, when you hear the word time-ordered product, just remember what they are. Now, how do we calculate it? What we did was we just, if you remember, we started from, we had an expansion, and from that expansion, we just combined them into this exponent. To actually evaluate this, what we will be doing is just start from this expression, expand it, take the first one or two terms, and evaluate it, and that would give you an approximate expression. Now, any questions?
Bir en alttaki değil, bir üstteki step'e geçerken.
This one. Okay.
Orada yani bütün integraller aynı oldu o zaman. Yani sadece enerji kuvvetini alıyoruz. Yani o zaman bunları time ordering yapmamızın bir anlamı var mı?
They don't commute.
Ama yani ben içeride gördüğüm ifade hepsinde aynı yani.
Well, let's see. What is an integral of an operator? It's just the sum of operators at different times. And then you are taking the power. Then there comes the ordering.
Okay, so I should do the time ordering. I should do the yani önce geleni ilk yapmam lazım.
True. You see, how do you define the integral? You just have this interval, you divide it into very small parts, and you evaluate that this time is your operator at each one of those parts. Now the question is, how do you sum them for an arbitrary operator? Yeah. Now, it's a good point. When you evaluate that integral, the operators are all the same. They seem to be, at least the result of the integral depends only on t, the same time. So what does the time ordering mean? And that's a good question. But keep in mind that these integrals, they're just sums of operators evaluated at different times. And then you need to take the nth power. And when you take the nth power, you will be multiplying operators at different times, and that's where the time ordering comes into the game.
I will ask again. Okay, so if already in integral that it will be like ordered in time, why do we have to put the time ordering? I don't know.
Well, you see, this time-ordered exponent, what you should understand from this one is just this expression. So at this level, it doesn't really make sense to write it in the last form anyway. So to use that, we have to use the previous expression, previous sum. We will go back to that. Now, the reason why I wanted to discuss this, which is not in your book, is that, if you are curious, if you in the future read about the field theories, this will be where you start from. And rather than evaluating it directly, you try to extract some of its properties of these time-ordered products. And then from those properties, you derive the Feynman diagrams. Now on Friday, what we will do is we will just go back to here and pick it up from there. This 2x2 matrix. Now, of course, in this 2x2 case, Now, this result is quite general for any system that will be valid. I mean, we never use the fact that it's a 2x2 system. But if you specialize to a 2x2 system, it turns out that you can, in fact, actually calculate this one, this h prime I. It will depend on time t. And in fact, the expression over here, this is the calculation of that matrix element anyway. So here we already calculated it. Question? Now, hopefully it will be more clear after your homeworks. That will come on this weekend.
Do you have an example in final lecture?
Sure. I mean, we will continue with this one. We will have an example.
Continue to derive something or continue?
No, I mean, we will just try to, I mean, the thing is, remember what we were trying to do. We want to study the evolution of a given system. So this two-body system is a simple system, but it doesn't mean it is not important. I mean, one known professor said that if you can understand the two-body system, then you know 80% of quantum mechanics, if not more. And I do think he is right, so this is what we will do. It's just a toy model we have in our hands, and we will see what we can drive it. So the question we would like to answer is this one. Suppose we have initially created a system in A state. What is the probability that at a later time we will be able to observe it in a B state? For example, the atom. So if you put an atom in a time-dependent electric field, that is, you have an atom, you shine a laser to it, that's the time-dependent electric field. So does it make a transition? What's the probability? Etc.
But that's not the two states.
Well, we will see that, and we will see that under which conditions we can treat that as a two-state system. We can treat it as a two-state system in a given approximation. If your laser light is not, the frequency is not that high so that it cannot excite excited states, just the first excited state, then it will behave like a two-state system. Okay, so see you on Friday.